Welcome to Tech Talks. I'm your host, and today we are diving into the world of quantum computing, where boundaries of science, technology, and innovation are being redefined. We'll explore how quantum physics differ from classical physics in everyday life and unravel what quantum computing really means for those new to the topic. Join us for an engaging conversation on how advances in science and technology shape modern world, right here on Tech Talks. So with me here today, I have
Andrew Chu, a Global Applications Manager in the Scientific Vacuum Division of Vacuum Technique.
I'm Hannah Vandenwijngaerden. I'm a Project Manager in the Scientific Vacuum Division of Vacuum Technique.
And I'm Jos Donders, Director of Business Development in the Scientific Vacuum Division.
Hi, everyone.
Hi.
Hi.
So, Hannah, this topic can be rather difficult. So maybe you can start by explaining what quantum is.
Sure. So quantum is the branch of physics that deals with matter and energy at the most fundamental level. So it's completely different to what we call classical physics, which is describing the world that we deal with in day-to-day life. So things like how a swing moves up and down, or how a thrown object might fall to the ground, or even how the planets move in space. But quantum, also called quantum physics or quantum mechanics, refers to the completely different physics that occur at the atomic and subatomic scale. Now, at these really small scales, physics becomes really weird. Things just don't happen as you'd expect. Some examples of that weird behaviour include wave-particle duality, where a particle can be a particle or a wave, depending on how it's observed, which I find very weird. There's superposition, which is where a particle can be in different states at the exact same time. And entanglement, where particles can influence each other no matter how far apart they are physically.
So, yeah, as you said, this is complicated already here. Anything you would like to add?
To give a bit of historical context, the word quantum was first put forward by Max Planck and Einstein in the early 20th century. And the exploitation of quantum was something that we saw maybe in the 1950s, 60s, where, for example, transistors were developed. But now to go to the full exploitation of quantum phenomena, we're in what's called the second quantum revolution, which, as well as computing, has great potential for things such as quantum sensors as well.
But then, Jos, could you maybe give us a simple explanation to what quantum computing is?
Yeah, what is quantum computing? In the end, it's about doing calculations faster than current classical computers can do. For instance, the status of quantum was always in a sort of a very R&D phase, and is now getting into this next phase of industrialization. Quantum computing is not as far yet as classical computing. There's still a lot of things to do to make it faster, quicker.
And what is then the difference between them?
The difference is that current computing systems operate with bits, 0 and 1. So you have a yes and a no. Future quantum computers work with qubits. A lot of qubits in parallel make the calculation faster. The problem sits is the errors that are come with that. And there is a lot of activity around error correction in order to make quantum computers viable with the right answers of these complex problems.
If I could just expand on that a little bit. So when Jos was saying about quantum bits or qubits, they're based on completely different physics. So whereas your classical bits can be 1 or 0, as Jos said, a qubit can either be 1 or 0 or both at the same time. And that's what's really powerful about it. It allows it to do more at the same time.
And is that why it's more errors to it today as well then, or?
I think the errors is about the quality of the qubit itself. So there's about 7 or 8 different routes called modalities in terms of generating qubits, and they all have their intrinsic capability of having errors associated with them.
Okay.
And as Jos said, there's a lot of work in terms of getting the full exploitation of the qubit to make qubits, a system of qubits, to make them fully usable, if you like, fully exploitable.
Mm-hmm. And how long have we been working with quantum computing? Is it a new technology or?
The first quantum computer was proposed by Richard Feynman, quite a famous physicist, probably in 50 or 60 years ago.
Mm.
And it's really, I think, in my opinion, probably about the last 10 years that we've had acceleration towards what is an attainable, functional, and exploitable quantum computers themselves.
Mm-hmm.
So we're very much in the very rapid growth phase, both from a technological and a commercial point of view when it comes to quantum technologies.
Mm-hmm.
There are in quantum sensors, which, for example, would allow positioning and navigation independent of GPS. These are already deployed for specific applications. So in a certain sense, quantum sensors show that quantum technologies in this second revolution that we're in is fully usable. Quantum computing, as Jos said a bit earlier, is a bit further behind.
Yeah, okay. And for what type of things do you use these sensors?
So quantum sensors can be used for things like navigation, also pressure sensing, location of objects. So, for example, looking at pipelines below the sea.
Yeah.
Quantum sensors are already here, they're already being used. Whereas quantum computers, we're making lots of developments with them, but there's not really any commercial quantum computers that are actively being used. There's sort of online...
you can access them.
You can access a quantum computer, but I don't think anyone owns a quantum computer at the moment. And I think there are certain people in the quantum sensing industry who get a little bit frustrated when people say quantum is how many years away, because for them it's already here. We're already using it. But quantum computing is just very different to quantum sensing.
Yeah. I looked at a TV show a couple of days ago, and they talked about the quantum computer at one of the universities here in Sweden, at Chalmers.
Yep.
But they have... From what I understand, they want to reach 100 qubits, but they are at 25 now.
Yeah.
So,
as the Atlas Copco Group, we are becoming an industrial partner at the Wallenberg Quantum Center in Gothenburg with Chalmers University. We're sponsoring a PhD there from the beginning of May. And the good thing for that is that we will also, as Atlas Copco Group, get access to the quantum computer that is running in Chalmers. So we have the possibility to have a understanding of what potentially it could be used in our Atlas Copco Group activities, from logistics, supply chain, all the other things that could be potentially beneficial from using such a quantum computer.
So I guess it's important to be part of this type of projects early on now, so you have access to it when it's ready to be used. Yeah,
so this is one of our part of our strategy, which is to try and identify and link in with these quantum centers of excellence, or the quantum hubs, to make sure that we understand what the direction that they're going is, what the pace of development is, and also what we need to do to be able to position ourselves to be able to meet the needs of these particular researchers, and how that will actually translate in the future to actual product sales. That's what we're trying to, and there are many of these centers around the world, but we've got a good understanding of what each one of them have got a slightly different approach.
Yeah.
And then we're plugging ourselves into them is what we're trying to do.
It's also sort of a development between hardware development and software development. It's really critical that these join up. So there is a lot of equipment needs to scale up the amount of qubits. At the same time, this topic about error and error correction requires very deep software development and algorithms and just AI and these kind of topics are very important to reduce the error rates over time. So you can scale up the number of qubits, but at the same time you need to also scale up the software to correct the error associated with the number of qubits that can exist.
Okay.
It's a truly multidisciplinary approach to actually bring a quantum computer to its full potential. Is a unique overlap of mathematics, computer science, new computer science, physics and engineering. And that's why you need these, like I say, multidisciplinary, multi-strand approaches to actually create something that's going to exist in a tangible form.
Okay. When people talk about quantum computing reshaping entire industries, what core capabilities are they then referring to?
The most powerful computers at the moment can model molecules for maybe 50 or 60 atoms. But when it comes to pharmaceutical development, you're trying to model molecules of hundreds, if not thousands of atoms. So the ability for a quantum computer to be able to deal with that type of modeling would completely revolutionize pharmaceutical development, both in terms of its complexity and also its timescales. Most powerful classical computer that we have at the moment, if you give it a very complex function, it could take several years, if not many years, to perform. A fully operational quantum computer could do the same task in 1 second. It's almost the scale of change is quite phenomenal. It can take 10 years or more to bring a new pharmaceutical to medicinal practice, and we could shorten that down by a factor of 10 or more. And many pharmaceutical companies are already looking into how quantum computing can be exploited to do this.
I'd say optimization is another one. So optimization looks at what is the best, most efficient way to solve a particular problem. And because quantum computers can be in multiple states at the same time, they're hugely powerful in these kinds of applications. So structures that might benefit from optimization would be things like supply chain networks, financial portfolios, traffic routing. I mean, the list goes on. But really, every industry would benefit from the optimization capabilities of quantum computers.
Defense programs. So you see cryptography. A key example, breaking the RSA code, as they call it. You see a lot of countries individually funding and sponsoring quantum programs for their defense industry. So whoever is first makes a big next step in that, and there goes a lot of work and funding in that area.
I think people do tend to be quite scared about quantum computers cracking all of our information. But it was a really obvious problem from the start. So people have been looking at it. And my understanding is that they have developed new algorithms and codes that are quantum safe. So I think it's called post-quantum cryptography. It just means a way to secure our information that's really safe from quantum computers. So it is happening. I don't think anyone needs to be worried about it.
Good that you pointed that out. Because it sounds quite scary.
Yeah,
when you read
does.
the media and you don't understand it fully.
Yeah, I can imagine people feel quite out of control because there's this really complex, difficult to understand concept, quantum computing, and it's threatening our secure information. If you don't understand it, how can you control it? But there are people who understand it very well.
Yeah. And then if we move on, what makes these systems fundamentally different from all other computing approaches? And maybe you, Hannah, can start here.
Yeah, sure. So there are other types of computing approaches that offer advanced efficiency and more power compared to our classical computers. So a couple of examples would be photonic computing and neuromorphic computing. And neuromorphic computing basically mimics how our brains work. So you have multiple neurons firing in parallel. That's obviously a really powerful way to compute things, but it's still fundamentally limited by classical physics. Whereas quantum computers are doing multiple things at the same time. So the analogy that I like to use is neuromorphic computers. It's kind of like giving a puzzle to 10,000 people and they all do a tiny piece of it. But that's completely different to a quantum computer, which is basically sort of, if you're trying to solve a maze, it's like looking at every possible path through that maze at once. Quantum computers are much more efficient in certain applications compared to the other types that I mentioned, like neuromorphic and photonic. But not all of them. There's just certain things that we're really excited to use them for, like the optimization and the pharmaceutical discovery and the cryptography and things like that. But not everything.
But looking into the future then, is a quantum computer something that everyone will have at home in the same way as we have laptops today?
I think we've got a bit of a disagreement about this, so it could be interesting. So the usual answer is you'll have quantum computers in like a equivalent of a data center, and then you'll have access through communication with that computer that will do all its power capabilities, and you do what you need done very quickly with it. But we used to say the same about classical computers. 50, 60 years ago or more, we'd say, oh no, there'd only be a few mainframe, big computers. But we've all got computers in our phone. We've got laptops. Everybody's got a computer if you think about many computers in the house. So I just think that maybe in 30 years, we'll all have inside our mobile phone some type of operational quantum computer. However, I know that others might disagree.
It's difficult to predict. I think you see the development, like Andy said, on data centers and the scaling and hyper-scaled data centers, lots of computing power. What is happening is that the combination of classical computers with quantum computers will happen. That combination will happen. Yeah. You hear a lot of things about GPUs, CPUs, QPUs, quantum processors, all that hybrid functionality. It's very likely to be a very remote access cloud-based solution for the future. And you have some sort of device where you can connect to.
Okay.
Yeah. I personally don't think that everyone will have their own quantum computer. I think the infrastructure needed to keep qubits stable is quite involved. So you often need cryogenics to make things really, really cold. So from what I've learned, it would just be huge overkill because quantum computers aren't better than normal computers at every single thing. There's only certain tasks that we would want to use quantum computers for, and I think the everyday person wouldn't really need to use a quantum computer.
No. So from your perspective, how essential are vacuum environments and related technologies to making quantum processes reliable and scalable?
Very. So vacuum and cryogenics, especially cryogenics at very low temperature. Quantum computers today, there are different technologies, modalities, as we previously said. And these modalities can be quite different from each other. One could work with extreme low temperatures. Others are operating in an environment of extreme, or what we call acute high vacuum. Very low pressures. And all of this has to do with keeping the environment clean for a stable operation of the qubit. All these systems that are there today will not be there tomorrow. So a lot of development will be required to scale up vacuum pumping systems, vacuum system designs, cryogenic system designs. that they operate very stable, reliable. Reliability will become very, very important. Systems will need to be operating in a stable form for a very long time.
Yeah.
So technology and reliability will go hand in hand there. And this is where Atlas Copco Group, we as a group, play a key role and are recognized in that area to help scaling up and to help the industrialization of quantum computing and quantum sensing and quantum communication applications.
Yeah. So Jos, you talk about very, very cold and also low pressure. How cold is it? And
we talk about very low temperatures, temperatures of 273 degrees below 0 degrees Celsius, close to 0 Kelvin, as one could say. Temperatures that create an environment that the qubits where they operate in can perform very stable. In other technologies or modalities, systems are developed at extreme low pressures, extreme high vacuum, acute high vacuum, very, very low pressures to do the same thing. Create a stable environment that qubits can operate in. We are doing the work to enable the industrialization, to develop the hardware in that environment, the pumping solutions, the cryogenic solutions. And one of the challenges is that going forward in time, products that are needed do not exist yet today. So a lot of development is required. Together with this technology scaling, you also need to look to the reliability and the stability of products over time, that they can operate in a performance that is very stable, but also survive. Its quality needs to be very reliable. So these things go hand in hand.
To add to that, can be a bit confusing, a bit contradictory in the way that we have our terminology. So in vacuum, we would say that the lowest pressures are at the highest vacuum. And so a low vacuum is a higher pressure. So it's a bit confusing. It's a bit of the way that we use terminology inside vacuum science. But when we talk about these really low temperatures, as well as the very low pressures, to give it an indication, we're trying to achieve 1 millionth of atmospheric pressure, and to operate continuously and reliably. Strange things sort of will happen there. We think we're going to have to develop new types of vacuum physics understanding. As we get to the really, really low pressures, very, very highest vacuum or acute high vacuum or below that, we're almost uniquely positioned to be able to do that in terms of our understanding and technical capabilities. But we really are pushing the boundaries. And it's as big a boundary step as during the space race when ultra-high vacuum was required. We anticipate as big a step forward is going to be needed to achieve these incredibly low operating pressures. We're getting into a situation where the volumes in the locality of a qubit, you have on average less than 1 atom per unit volume there. So that brings in almost a philosophical question about what is actually happening in those types of rarefied atmospheres. So it's an exciting time. And we realise we've got great skills within the group, Atlas Copco Group, to do that. But it's one of the reasons that we are working closely with a lot of third-party academic partners who have much more specific skill sets in elements of that. What we're trying to do is to bring them all together, understand the requirements and how to, as Jos said, how to come with a technical engineering solution for the technology base, and also how to therefore understand what's required for our products in the short term and also in the long term to give us an advantage.
Looking ahead, which breakthroughs in qubit technology, error correction, cooling, or modular design do you think will drive the next big leap in quantum computing?
I think that the next leap in quantum computing will come from error correction, because today's quantum computers are incredibly sensitive. So things like heat, vibration, electrical noise can completely disrupt a calculation. An analogy that I like to use is like having to whisper at a rock concert because you don't want to disrupt the band. That's how sensitive they are. And error correction is the process that we use to try and catch and fix any mistakes that come from tiny disturbances. And unfortunately, just for one, what we call a logical qubit, just for one thing that can do a calculation, you often need dozens, if not hundreds, of physical qubits to try and correct. And that makes it so difficult to scale up. So if you want to get to 100 logical qubits, you need, hundreds of times that in physical qubits. But I think advancements in error correction that make that much more efficient will make it truly scalable, and it will take it from like a fragile lab experiment into a sort of commercial technology.
I think the answer is I'm not sure. There's 8 or 10 different, as Jos mentioned, modalities, different routes to trying to create the kernel of the quantum computer. They all have their advantages and disadvantages, but we're at the very, very bottom of the steep curve up to the top of the mountain, a quantum mountain, where we're trying to get to 1 million qubits, operational logical qubits. And we really probably got maybe at best 150 or 100 at the moment. So there's a huge amounts of work to do and a lot of unknowns. The good thing for us is that each of these different techniques, each of these different modalities represent to Atlas Copco Group an opportunity for deployment of our vacuum and cryogenic technologies.
Yeah, I think also the equipment, hardware, and the different technologies. So we cannot bet on one horse from an Atlas Copco Group side. So we like to be engaged with all the different modalities. And the good thing is it's all about vacuum and cryogenic. So we're in that space. Like Andy said, the amount of qubits that are operational at the moment with a certain error are in the 50 to 100s to become quantum advantage. When a quantum computer becomes faster than a classical computer, probably takes another few years, let alone to be what they call fully fault tolerant, which is expected to be at 1 million qubits. So the roadmap towards that journey from 100 to 1 million goes in steps. And you see the key companies working on this, they work in milestones. And we trying to bridge that milestones by equipment development, meeting these timelines, and then scale the amount of qubits over time with the equipment that we can offer in that environment. This is where I think we, as Atlas Copco Group, can play a key role.
So we are both supplying this technology with our products, but we also need it for ourselves in the future to be more efficient.
Absolutely. Yeah, in our daily life, but also in our supply chain, in our logistics, in our way of working. You can deploy quantum computers just like we do today. It will probably be different than how we use computers today, but it's definitely an internal feature to use quantum computers in the future, as well as that we can supply products in that market.
So finally then, what drives your passion for working with this technology, and what keeps you energized as this field evolves so quickly?
I think for me there's two things. So first, as someone with a background in physics, it's really exciting to be working in this quickly evolving field that's based on the physics discovered just 100 years ago. But secondly, working in the Atlas Copco Group, which contains a lot of vacuum and cryogenic companies, we're uniquely placed to provide a solution to this huge new market that's coming out. So we could potentially offer systems for these customers. And for us, there's the opportunity to develop entirely new product lines just to serve this market. And I don't know if it was mentioned before, but I see it as being really similar to the 1960s space race. So whereas in the 1960s, vacuum companies were being asked to develop new vacuum technologies so we could get to the moon, Now we're just being asked to develop higher and higher vacuum environments, so lower and lower pressures, to keep qubits stable.
Well, from a physics point of view, I like to say that I've been not understanding quantum physics for nearly 40 years. But certainly the acceleration in this field in the last 10 years, if not even indeed the last 5 years, is really exciting to be part of the program of work that is actually taking these things to what was not too long ago just esoteric types of thought. They were just ideas, theoretical ideas, and now to actually be part of something where we're actually very close to fully operational quantum computers is really exciting. It's quite something to be part of.
Yeah. How about you, Jos?
I think the people are really having listening ears. A lot of discussions, and also internally, people are also eager to help developing product in that environment. You see, we're really in the middle of that. A lot of passion, a lot of energy, which keeps us energetic in that environment, I think.
Yeah. And that you can hear from the discussion we have had today, that there's a lot of passion behind it.
Yeah, definitely.
And also, as you say, a lot of people want to be part of the race, I understand, of this new technology. That wraps up today's discussion on quantum computing. If you'd like to learn more about us, visit atlascopcogroup.com. Stay tuned as future episodes dive deep into technologies that transform the future. A special thanks to Jos, Andrew and Hannah, and for all you listeners tuning in. Take care and see you soon.